Yeah, perfect. Many thanks, and thanks for having me here. This is not the official title, but it just reflects that when thinking about a subject to tell at this meeting, what came to mind was a story combining the physics of the SYK model with that of many-body localization, or more accurately, Fox-space localization. Just knowing that many of the people here are working on either one of these subjects or indeed on both. I would also like to mention that on the methodological side, the progress we made is based on pioneering work by the French field theory group, in particular matrix field theorists, and that includes prominently Claude Itzigson. And I thought that was another befitting point. Now, after let me cut right to the chase and introduce our protagonist today, the SYK Hamiltonian. As many of you will have seen it, a system of 2n Majorana fermions, or equivalently n complex fermions, strongly self-interacting via an interaction which is entirely random and governed by randomly chosen interaction constants. This is a plain vanilla SYK. It's not quite enough for our purposes. What we need to add is seemingly innocent free fermion part, a one-body operator, so that we have an SYK4 plus SYK2. And this one-body term we assume to be pre-diagonalized. So it's governed then by n, again, randomly chosen coefficients, something like one-body potentials. And the point now is that these two are in competition, and this competition defines a beautifully realized many-body localization transition. Before discussing this in the specific context of the SYK model, let me recap or review, for those of you who are not so familiar with MBL physics, the basics of this transition in the simplest possible way I can. And that essentially amounts to retelling the story of a classic paper, Altland, Geffen, Kamenev, Levitov, 25 years back. I think a paper which started MBL as a field. And what they were doing, they were looking at an interaction Hamiltonian of the same architecture as the SYK Hamiltonian, free fermion part plus interaction. No spatial structure here. And the first thing they tell us is that you better think about this problem in a first quantized representation. And if one doesn't do it every day, it takes a bit of getting used to, but this is the preferred language here. And in this setting, the Hamiltonian simply becomes an exponentially large matrix, a 2 to the n dimensional matrix, acting in a Fox space, which has a natural structure of a hypercube, defined by the binary occupation number sites of our n fermions, so these 0-1 combinations. And on this lattice, we have, if you will, a random potential, a local potential defined by the non-interacting part of the Hamiltonian. And this potential, importantly, and that gives the problem part of its complexity, is not statistically independent. It's massively statistically correlated. The point being that we have only n randomly chosen coefficients, these VIs, from which we dial up 2 to the n local Fox space potentials. And this potential is now in competition with the interaction operator, which here plays the role of a hopping operator. It's a distance 4 hopping operator, meaning that it changes only 4 occupation number states at a time. And this competition now defines the transition, and where this transition actually takes place can be understood quite easily on the basis of simple quantum mechanical perturbation theory. So to this end, let's just pick two sides on our lattice connected by an interaction matrix element of typical strength T. And what we can say is that a wave function will hybridize over these sides and be extended over these sides if the energy mismatch, which is given by the difference in their one-body potentials of order VI, if that mismatch is give or take of the same order as the hybridization strength, which is set by the interaction. Now, this stringent hybridization condition need not be satisfied for all pairs on our lattice in order to form an extended state. The point being that individual sites have many, many nearest neighbors. I call it M here, the number of nearest neighbors, which is of the order of n to the 4, so algebraically many in n. And for a state to be delocalized, it suffices if any one of these nearest neighbors actually gets hybridized. And that leads to a criterion, zeroth order criterion for the localization transition, M, number of nearest neighbors, times T over delta B of order 1. Now, this was a very primitive argument, lowest order perturbation theory, but you can refine this within the context of this phenomenological lattice approach by including higher generations in perturbation theory. What you get in return is just a logarithmic renormalization. So the argument more or less has it right. So M log M times T over delta of order 1 is the critical threshold for the transition in this kind of estimate. So this was very schematic, and what I would like to do in the main part of the talk is discuss the physics of this transition for the SYK system. And let me therefore try to give you an impression of the real SYK Fock space, in quotes. So this here is a more or less faithful representation for 14 Majorana fermions or 7 complex fermions. So we have 128 sites. And what I've done is I picked one site and indicated all other sites connected to it by the SYK4 interaction. And that should give you an idea of the nature of the problem. So we have a kind of smallish lattice, which, however, is densely packed. It has exponentially many sites on a lattice of linear extension n. The disorder I mentioned is strongly correlated, and you have a very high coordination number of order n to the 4. Now, this sounds like a complicated problem, but this high coordination number is in fact the Achilles heel of this problem. I mean, it introduces a fair degree of self-averaging into this problem, which actually gives us the traction necessary to largely solve it analytically. And that's what I would like now to discuss in the rest of my time. I want to look at this transition quantitatively in this SYK setting. And I think I should first give you a little bit more of motivation of why this might be an interesting exercise. And then I say a few words on how we actually do this matrix integral framework, which I mentioned in the beginning. And in the main part of my time, then discuss results for this type of Fock space transition. So, question, why would one want to look at MBL in this particular context? I see 2 main motivations for that. The first is kind of simple. Everybody working in MBL knows that this is really a tough problem, and we have very few, if any, really explicitly worked microscopic model solutions. Now, the SYK Hamiltonian gives us, I believe, the simplest model where real MBL can be observed. So I understand it is a kind of a null model or harmonic oscillator in this field. And it is just simple enough that you can actually do something analytically from first principles and compare to efficient exact diagonalization in a way that the two can actually be compared without parameters. So this gives us some kind of test of our theory. Those of you who have been here yesterday and heard the talks by Tomasz and John may wonder how all this compares. We should have in mind that we have a 0-dimensional system here. So this is way simpler than the 1-dimensional MBL problems that were addressed yesterday. At the same time, we don't take here what Tomasz called a thermodynamic limit. So we work at large but finite n. So the Heisenberg time, if you want, is not sent to infinity. And in practice, this means that this problem has much stronger quantum fluctuations, which cannot be brought under control by semi-classical arguments, by counting path and so on. So it's kind of a bit of a trade-off. And that's that. And there's a second motivation for all this. The transition has a delocalized side. And this delocalized side is kind of interesting, certainly more interesting than in one-body localization problems. And to understand why, compared to a one-body problem, say a disordered metal, where you could have a localized wave function and a delocalized wave function. And delocalized wave functions, in this case, typically uniformly cover space. So they're in this sense trivial. But not so in Fock spaces. In Fock space, there is again a localized phase, but the delocalized phase, and this follows from the argument I gave you earlier, it actually, in the delocalized state, the support set of wave functions starts to shrink long before they reach the localization transition. So there is some kind of non-trivial support set interlaced into Fock space. And this gives us a whole lot of points we should want to explore. First of all, it should be evident that there are, broadly speaking, 3 different regimes, or maybe even phases, to distinguish. The extremes being the strongly localized phase, which we do not focus on now. On the opposite extreme, we have the trivially ergodic phase, I mean, where there is no one-body term, essentially everything is interactions, wave functions are totally uniformly spread out. But in between the two, there is an extended regime, which we call for internal reasons 2 and 3, because in fact it splits into 2 regimes, but that's a detail now. But anyway, there is an intermediate regime where wave functions are extended in Fock space, but non-trivially so. They do not cover all of it. And this gives now room for a whole lot of possible scenarios. And broadly speaking, there are 2 of them, which one may distinguish and which have been distinguished in the recent past. One is where the kind of anticipation that wave functions get non-trivially extended, and non-trivial here means non-trivial distributions, typically multifractal distributions. So people have, there is perhaps this dubbed phase of non-ergodic extended states characterized by multifractal support sets. Then there is a more conservative reading where you say that there is in Fock space some kind of, is there a question? Oh, here? By the way, if there are questions, if our chairmen don't mind, ask them right away. Yeah, I mean, I think it's maybe better. Scenario number 2 is where you have some kind of energy shell in Fock space, and on it, wave functions remain ergodic. In a sense, we should want to make more precise. Now, at this point, there seems to be a growing consensus that number 2 is a more physical scenario, but still there are questions one should ask and answer. Number 1 is, what is this bloody energy shell? I mean, how is it embedded in Fock space? And number 2, how are wave functions distributed on this shell? I mean, are they, in quotes, just thermal states, or are they maybe in more interesting ways internally correlated? Now, before answering these questions and addressing them for the SYK, let me quickly introduce the tool set, I mean, by which we can address such questions. And many of you know that, but for the non-experts, the extension of wave functions in many-body spaces is commonly probed by inverse participation ratios. These are simply high moments of wave functions in a preferred basis, which in our case is the occupation number basis. And why these are good quantities to consider simply follows from considering extreme regimes. If wave functions are super localized in Fock space, these participation ratios assume a value close to 1. And if they are uniformly spread, they assume a value by wave function normalization of 1 over cardinality of the support set. So in this sense, they give us a good order parameter testing the structure of wave functions, where the distribution, or more precisely the entanglement properties of wave functions on these sets are considered. We need a different diagnostics, and these are entanglement entropies, a standard concept. We consider pure state density operators, monitor them in a preferred basis, introduce a subsystem cut in Fock space somewhere, and then study entanglement properties. And you can ask yourself, what kind of answers should we expect for these guys? And candidate answers that come to mind are, number 1, the thermally distributed states. That would be, I mean, for Majorana fermions, just log of the Hilbert space dimension of the subsystem. But we know that this can't be the full answer. There is classical work by Page, 93, who studied entanglement properties of fully random states. I mean, states that are as random as they come, and found that there are corrections, universal corrections to thermal distributions, which are super universal. They involve only the dimension of the involved spaces. And we can ask if this is the end of the answer, or maybe actual states in real many-body systems do something perhaps even more interesting. So that's basically our starting point. I brought up a few questions and the tools by which we can hope to answer them. And I want to get now a little more specific, not a little, a lot more specific, and consider really the SYK model. And well, let me first say a few words on how we approach this system. This is just throwing a few concepts at you. I don't want to go into any detail here. So we approach this problem by replica field theory. We map the SYK or the computation of SYK correlation functions onto a replica matrix integral, averaged over the SYK interaction Hamiltonian, but evaluated for a given realization of the one-body term. This is technically an important point. We don't average over the one-body term at an early stage. And then we crank the machine. We do a stationary phase program, which actually is not so super well controlled. So that's something one should keep an eye on. Introduce fluctuations around these mean fields and map the whole thing onto an effective path integral for these fluctuation matrices, which is then analyzed by tools standard in the field of localization theory, especially on high-dimensional lattices. Keywords are effective medium approximations, which are philosophically close to DMFT. So this was just a bit of name dropping to give you an idea of what kind of concepts we apply. And let me now turn to the discussion of results. So the first is the localization transition itself, and in particular, where does it take place? I mentioned earlier this kind of phenomenological n log n estimate. We find something slightly different. We find the localization threshold independence on the disorder strength and on the particle numbers, which involves a special function, a Lambert W function, which only in the thermodynamic limit of a very large n asymptotes to n log n. So that's a quite definite prediction. And this is something we can now test numerically. And we do so by comparing to not one, but two observables. The first are these inverse participation ratios, which I mentioned earlier. And the second is spectral statistics. So we know that on the delocalized and localized side of the transition, we should expect Wigner-Dyson and Poisson statistics respectively. And in a super perfect world, we would, for a disorder strength scaled by this prediction, observe a crossing at the same point unity. And we don't quite get it. I mean, if you look at these two plots upstairs and downstairs, you see that they kind of sort of cross at a value which is off by a numerical factor 3 or 4, which we don't understand. We have no idea where this factor comes from. Maybe it's a computational error on our side. But otherwise, the scaling is kind of good. And it is qualitatively better, and that's now my main point, than scaling in terms of this n log n estimate. So if you try to scale the data by n log n, you will not be able to scale inverse participation ratios and spectral statistics onto the same point. So that gives us some confidence that this quite sensitive prediction here, this Lambert W function, which follows from the field theory after a long calculation, is actually a good one. And I should like to emphasize that there is zero fitting parameter here in this comparison. So it's kind of a relatively stringent test that the localization transition, its position is under good analytic control. Now, on this basis, let me now look at the localized phase and address these issues of fractality or no fractality. Here, I mentioned them, the inverse participation ratios are center stage. So we have them and we can compute them from our field theory. And these are the predictions for the ergodic regime, respectively, where we have essentially no one-body term, and then these intermediate regimes. And you don't; these results don't mean anything to you if you look at them, but they become a little easier to digest if you evaluate them in the limit of large Q, I mean high moments of the wave functions. And they then asymptote to a really simple prediction. The inverse participation ratios scale as moments of 1 over an effective support set extension. So what this means in simple language is that the support of wave function continuously diminishes from full coverage of the Fock space down to an algebraic fraction of it, n to the minus 5 halves close to the transition. But importantly, this is not a reduction in which is exponentially strong. It's a strong reduction, but it's algebraic in n, not exponential in n. And that means that we see 0 indications for multifractal behavior in the system. I don't think there is any multifractality here on the delocalized side of the transition. And maybe this doesn't mean much for you who aren't in this field, but there has been quite a heated discussion of this point recently, and this is what we get for SYK. Here's again numerics. These are the inverse participation ratios numerically observed for systems of up to 30 Majorana fermions compared to these analytic predictions. The focus is here on this regime 3, intermediate disorder strength. The agreement is again quite good. There is no fit parameter again. We see here for large n, 15, we see that there is a deviation mounting. The actual numerical curve gets a little steeper. This is not an error. It simply means that we are seeing critical signatures of the approaching transition eventually for n to infinity, which nobody can do numerically. There would be a kink forming in the inverse participation ratio at this point. Okay, so this was the participation ratios. And now let's ask for the entanglement properties of states on these energy shells. And again, there is an analytic side of it. In regime 1, which is a trivially ergodic regime, we find the page result, which we should. I mean, so the states behave like pure random states. I mean, they are just uniformly, purely random distributed, and we have a slight deviation from the thermal entanglement. Regime 3 is more interesting. There we see a stronger, and for small system size cuts, exponentially stronger correction to thermal entropy, which is super universal. It involves, again, only the dimensions of the subsystem Hilbert spaces, but not the disorder strength or other system parameters. And what this reflects is the internal correlations of the energy shell in a way which I just don't have the time to discuss in more detail. And finally, in the localized regime, the entanglement simply breaks down because the energy shell fragments. This again, we can test. So these are entanglement properties now for weak disorder, which are these boxes here numerically. Delta, the disorder strength is very weak. We obtain numerically and analytically super good agreement with Page. And for in the non-trivially ergodic regime, we get our other formula. The agreement with numerics is again quite good, I think, except for a mismatch, a mounting mismatch for large system sizes. For the smallest system size cuts, I mean 1, 2, or 3 bit systems, deviate strongly, and we have no clue where this deviation comes from. We just don't understand it. But otherwise, I think the agreement is pretty good. Take-home messages, at least for me, I mean, what I learned from this is, and I think this extends to delocalized states of many-body chaotic quantum systems with long-range correlations in general, not just SYK. First of all, one thing I learned is that it really pays to look at both at inverse participation ratio, which is common in this business, and entanglement properties combined. And on this basis, we conclude that there is really a notion of qualified notion of ergodicity, no fractality. And these states are a little bit more intelligent than states, fictitious states, which would be just thermally entangled. I mean, they have these these correlations which are indicative of what is going on microscopically. That's an important point, actually. If you look at synthetic high-dimensional random lattices, which people often do to study localization properties, I mean, keywords are random regular graphs or other beta lattices or other high-dimensional lattices, their states have totally different entanglement properties than those we are having in real systems. So in this sense, it's an interesting observable to look at, including for other systems than SYK, I think. Yeah, and this was basically it. So I think, or I hope I'm able to show that the SYK model actually, what many of us love for different reasons, is a good test bed, including for Fock space localization. I mean, it's a very nice system to test concepts. I've emphasized here the point of ergodicity, which I think is really established in this system. The obvious question to ask, an elephant in the room, is can one generalize this to higher dimensions? And well, I mean, I don't know, and it's not for lack of not trying. I mean, one could think or hope that one can address a spin chain with local interactions by the same methods, but we really don't understand MBL in these systems, and I think we need fresh ideas, maybe ideas along the lines of what we heard yesterday by John and Tomasz, and marry them with the microscopic techniques we are applying here. But so far, this is an open problem, which makes one ask if there is relevance to all this beyond the obvious academic interest of understanding these types of transitions. And there the answer is actually yes. I think there is strong relevance of these concepts, and this is no joke now, to applied quantum computing. And the point here is, and this is just a teaser, I mean, if you are interested in this, that if you look at current day transmon architectures in the industrially or produced transmon chips by Google or IBM, they are operated in MBL phases. And that's as a matter of principle. You need the MBL phase to protect the stability of these systems. And they are small sized. So they are really systems in the ballpark of these small size extended systems we're looking at here. And what one can do, and what we have done, in fact, is apply these concepts, inverse participation ratios and entanglement properties and so on, and investigate them for these systems and monitor their stability in this framework. And, if you're interested, here's advertising. And with that, I think I would like to close, and thank you for your attention.
Thank you very much, Alex, for the nice talk. You can unmute to up. So we have time for questions. You can unmute yourself, maybe ask if you want, or raise your hand. Otherwise, I will start maybe with the question. So, Alex, I have two kind of related questions. So you mentioned at the end connection with random regular graph. I was wondering, so there are models like the quantum random energy models in which people have looked for non-ergodic phases. Can you comment on the entanglement? Do you have an idea of whether these are different with respect to your SYK result in terms of entanglement properties?
Yes, they are totally different. In random energy model, you would not find these strong corrections to the page formula.
Yeah.
And in fact, I mean, historically, we first thought we had an early paper where we did SYK, I mean, random energy model for SYK, and only later did we understand that the real thing is actually quite different, and it's tougher to describe. And the entanglement properties is one way they actually deviate from the.
Is this because of the uncorrelated energies of the
yeah, indeed. So the physical origin of this kind of entanglement contribution is that you have a conserved quantity with subsystem additivity into the system, so which in this case is energy. This is one, I mean, you would, for every conserved quantity, you get an additional contribution of this type. So you have energy of system A and system B, and they are additive. And this is the principle which generates this mechanism of entanglement. You don't have that in the RLE.
I see.
Yeah.
More questions?
Yeah, I have one. Alex, thanks for a nice talk. Maybe you've mentioned it, but I missed it. But can you compute the distribution of matrix elements across the transition? Let's say I take some simple operator.
Mm-hmm.
Right.
Yes, I think I think it's in reach. What we can do, we can compute anything that's expressible in terms of the resolvents of this full Hamiltonian. Yeah? So if you give me some operator and I compute a correlation function which is then expressible in terms of resolvent, and these are the many-body resolvents. Right? We are in business kind of. Right, more intelligent observables we can't, but and maybe to add one thing we have not done, we didn't even attempt to, was to discuss critical phenomena. I mean, like scaling properties across transition, simply because the comparability to numerics for these system sizes would not be good enough.
I see.
Thanks.
More questions? I have another one, if I can. So in this mixed SYK4, SYK2, I remember there were papers talking about, maybe also from your group, talking about the transition between a finite n, between a delocalized, between ergodic and something else. Is this now MBL transition you're talking about here the same thing? Do I understand that correctly? This one transition a finite n, or that's
yeah, I mean, my understanding is eventually you have to go if you want to see a transition in the textbook sense, you have to send n to infinity, and then you actually, but so this scaling in n is like a finite size scaling for this type of transition. But with this in mind, I think, yeah, this is the same.
Okay.
Yeah.
Okay.
Mm-hmm.
Okay, good. Any other questions? Otherwise, thank Alex again.
Okay.